In this video, we're going to learn about the final quantum number that is used to describe electrons, specifically the movement of electrons, which is why we refer to it as the spin number or spin direction. In order to answer what spin direction is and why it's important, we can ask three simple questions. Number one, do electrons ever stop moving? Well, that's a pretty solid no. As long as they have kinetic energy, electrons will keep moving indefinitely. Number two, if you have two electrons that exist within the same orbital and form a pair, do they want to stay with each other? Well, since they both have negative charge, they're going to repel away from the other, and the answer is again a hard no. Number three, if two electrons were in the same orbital, does it make sense that the two electrons would ever move in the same direction? In other words, if the electron on the right moved to the right, would the electron on the left follow it and move in the same direction? Again, this doesn't make sense because electrons have the same charge and tend to always repel from each other. Therefore, this doesn't make any sense either. This is why spin direction is important, because electrons should never be moving in the same direction as each other. Which brings us to how electrons actually move. When electrons move, they move the same way that ping pong balls or baseballs do in their respective sports. They move by spinning and twirling in that direction. So with this electron here, if we trace its spin direction, we see that that spin direction moves in an anti-clockwise direction. Again, the opposite direction as the hands move on a clock. Conversely, this electron, if we trace its direction where it spins to move, this is what we call a clockwise spin, because the electron spins in the same direction that the hands of the clock move. This spinning gives each electron a small magnetic field. That's where the charge of electrons comes from, in the same way that when the Earth spins, that creates our magnetic field that our compasses depend on. Now, in order to show this, remember that we cannot see electrons. We can't even predict where they're going to be, but we do know, depending on the spin direction, which way their magnetic fields face. So in the case of an anti-clockwise spin, we see that the magnetic field is pointing upwards, which we represent with an up arrow, while a clockwise spin is the opposite direction for its magnetic field, which is why they point down. We can use this information in the final way to represent electron configurations, which are what we call orbital energy diagrams. On paper, orbital energy diagrams just look like a bunch of boxes with arrows, but each box represents an orbital. Knowing that, they actually make a lot of sense. So, as we've determined, electrons that exist within an orbital should never be moving in the same direction, which means their magnetic fields should not point in the same direction. So if this orbital had a pair of electrons in it, one of them would have a top spin, and one of them would have a backspin, showing that they're moving in opposite directions. If we apply this to an actual element, in this case nitrogen, we can draw our subshells and orbitals to match this. So one box represents the 1s subshell, the next box represents the 2s subshell, and because a p subshell has 6 electron capacity in total, we can break it into 1, 2, 3 orbitals like so. Then it's simply a matter of filling in the number of electrons per box. We see 1s is full, so 2 electrons with opposite spin direction. The 2s subshell also fill 2 electrons with opposite spin direction, and we remember electrons do not want to pair with each other unless there is no other choice because of repulsion, so let's put 1 electron per p orbital like this. Fortunately, with elements with a large number of electrons, we can also use core notation as a short form. We remember that the closest noble gas to nitrogen that isn't larger is actually helium. So we can represent helium here in brackets to represent our core, and we know that the electron configuration of helium is 1s2, and the rest of the electrons we represent in the same way, drawing the 2s subshell and the 2p subshell exactly the same as before. Now that you've seen how to do orbital energy diagrams, it's time to retroactively apply a few rules for it. The first of which is the Aufbau principle, which simply states that orbitals are filled from the lowest energy level to the highest. And we know the lowest energy level is always going to be 1s, so that simply means we start filling orbitals from the 1s subshell and gradually ascending higher. Hund's rule is the rule that explains that we cannot pair electrons within an orbital until each electron each orbital rather in the subshell is filled. So each subshell must have one electron per orbital before electrons can form pairs. And that's again why each orbital needs one electron in it, or each orbital in the 2p subshell rather needs one electron in it before we can start filling pairs. Number 3 is the Pauli exclusion principle, which states that no two electrons can have the same quantum numbers. In other words, no two electrons can be in the same subshell, in the same orbital, and with the same spin direction. And a more succinct way of putting this that's relevant to us is this rule here that states that two electrons in the same orbital cannot have the same spin direction, because as we established, that doesn't make any sense based on how electrons move. For practice, you can practice writing out both the standard form of orbital energy diagrams for the elements below and then convert them into core notation. In the final video, we are going to take a look at quantum numbers and the actual way of using the numbers to represent different characteristics of the elements or of the electrons that each element has.